Okay, so now let's move on to a couple of practical examples. So we have one where you can make a rod move and another one where you can generate electricity using induction. So in this case, what I have is this gray bar has zero resistance and it can slide back and forth on this rail of the two darker rods. Okay, so the zero resistance rod slides to the right in the direction shown by the green arrow there, on two rails separated by a distance L of 0.45 meters. So we've got this distance here is 0.45 meters. And the two rails are connected by a 12.5 ohm resistor. That's over there on the left. So R is equal to 12.5 ohms. And the entire system is in a uniform magnetic field. So it's shown by those dots with the circles around them, with a magnitude of 0.75 Tesla. So let me write that down. B is equal to 0.75 Tesla. All right, so I want to find the speed at which the bar must be moved. So I want to find V, so I'm looking for V, in order to produce a current, so that's I of 0.125 amps in the resistor, and I also want to know what direction is the current flowing through the resistor. So here I have the B is coming perpendicular. Those little dots with a circle means it's coming out of the page, so it's coming perpendicular to the loop. And the loop here, let me draw it in red, the loop here is defined by the area that's enclosed by that rectangle. So when I move the rod over towards the right, I'm making that loop bigger and bigger. So I'm going to have more and more flux, more and more magnetic field lines going through it. So I have an increasing flux. So we're going to use that to answer part B at the end to figure out what direction the current will flow through the resistor. All right, so let's start off by thinking, what do I want to find? I want to find V. So what equations do I have? Well, for a moving bar, we have the equation that the voltage that's generated by a moving bar is equal to the size of the field, B, times the length of the wire, L, length of the moving bar, and it's times the speed. So I want to find V. Okay, so that's what I'm trying to find. I know B and I know L, but I don't know my voltage. Is there any way I can find the voltage? Well, what else am I given in the problem? Well, I'm given, I know what the current is, and I know what the resistance is. So I could use Ohm's law. So I can use V equals IR to give me what the voltage is. So my voltage is 0.125 amps times my resistance. Let's see, I didn't calculate that, so let me bring up my calculator. All right, so 0.125 times 12.5. I get 1.5625 volts. All right, so my EMF that's generated across that resistor from one point to the other is 1.5625 volts, and that's going to be the same as what's across the rod. All right, so I know my E now, so now I can calculate my V. So rearranging that equation, V is going to be equal to E divided by BL. So my EMF, now I'm just going to plug and chug, is 1.5625 volts divided by B, 0.75 Tesla, times L, which is 0.45 meters. And I get a velocity of 4.63. And let's see, I've got some of these are 3 significant figures, and some of them are 2, so I got to round to the smallest number, so I got to round to 2. 4.6, and the units for velocity are meters per second. Okay, so next thing, so that's my answer to part A. Part B asks, what direction is the current flowing through the resistor? So now we've got to do Lenz's law. All right, so what's happening here? Well, the area of the loop is increasing, so we know that the flux is increasing. The amount of magnetic field lines is going to go bigger as the area increases, and it's increasing out of the page because that's the direction that the field is going. So what happens? Well, Lenz's law tells us that the loop wants to keep the magnetic field through it the same. So if the field through it is increasing, it wants to create a field in the opposite direction. So the induced magnetic field is going to be opposite. So that's going to be going into the page. So how do we figure out what direction the current flows through it? What you do is you take your right fist, so make a fist, put your thumb in the direction of the induced field, which is in. So when you put your thumb in, you find that the current is going to flow in the direction of your finger. So current flows clockwise. All right, so if I go on my loop and I make the current flow clockwise around the loop, so let me keep doing it in blue. All right, so current's going to flow clockwise around this loop. So that means when it goes through the resistor, it's going to be going from the bottom to the top. So the current flows up. Through the resistor. So up towards the top of the page. Okay, so make sure you practice Lenz's law problems. There'll definitely be something on the test asking you about what direction the current will flow in a loop if you change the area, change the field, change the angle, etc. All right, next question is a generator question. So a generator is designed to produce a maximum EMF. All right, so write this down, Emax of 170 volts while rotating with an angular speed of 3600 RPM. So omega is equal to 3600 RPM. So remember, this is pulling us way back to, let's see, what was it? Chapter 8 in Physics 1, right, where we talked about angular motion. Each coil in the generator has an area of 0.016 square meters. If the magnetic field is 0.05 Tesla, all right, so I'm just going through pulling out every number I have. How many turns of wire are needed? So turns, that's capital N, so I want to find N. All right, so what's my equation? Well, my equation for the voltage created by a generator is that it's equal to NB A omega times sine of omega t, where this number out in front, that combination of constants in front of the sine function, so remember a sine function goes like this, between +1 and -1, so the maximum value is going to be determined by those constants, right? So it's going to be plus or minus 1 times those constant. So Emax is just those combination of variables out in front. So what I know is that this combination has to be equal to 170 volts. I want to find N. We're given the field, we're given the area, and we're given omega. All right, so I know everything. So I know Emax is equal to NBA times omega. I want to find N, so N is equal to Emax, which is our 170 volts, divided by B, divided by A, divided by omega. So we're pretty much ready to plug and chug, but we need to remember that when we talked about it in Physics 1, omega should have units of radians per second. And in the problem here, they gave us it in revolutions per minute. So I'm going to have to do a conversion. All right, so let's do a conversion just like we did way back in Module 1 of Physics 1. So let's write down what I have, 3,600 revolutions per minute, and I want to go to radians per second. So let's do first a conversion. Let's do minutes to seconds. All right, so I want to have minutes on the top and seconds on the bottom, so that will allow me to cancel out the units of minutes. Okay, so 1 minute has 60 seconds. So I'm going to put 60 with the seconds and 1 with the minutes. All right, so now I've got revolutions per second. I've got to convert revolutions to radians. So I want radians on the top and revolutions on the bottom. So then that will allow me to cancel out the units of revolutions, and that will leave me with units of radians per second. Right, so what do we know? Well, a revolution is 1 time around a circle, and 1 time around a circle is 2 pi radians. Okay, so 1 revolution is 2 pi radians. So now I'm going to take 3600 times 2 pi divided by 60, plug that in my calculator, and I get 377 radians per second. So now I'm ready to go and just plug and chug into that equation that I have up at the top. So let me go do that. So I've got E max is 170 volts over B, which is 0.050, times A, 0.016, divided by omega, 377, and I get that my N, the number of turns that I need, is 564 turns. So that means I need to wrap the wire around 564 times. I need to make that number of loops in my generator.